All right, now that we know how to set up a triple integral in spherical coordinates, let's practice. So let's take this function and integrate it over the unit ball in 3 dimensions. The unit ball is just a solid sphere of radius 1, and a sphere is most conveniently expressed in spherical coordinates. Surprise, surprise. So here's a sketch of the ball. Let's try and represent the solid ball in spherical coordinates. Well, the row values of the points in this ball are going to be in between 0 and 1. And then the phi coordinates extending from the positive z-axis down to the negative z-axis are in between 0 and pi. And then the theta, which goes around the equator direction, range between 0 and 2 pi. So this is the description of the unit ball in spherical coordinates. That's step number 1. Now we have to take the integrand function and convert it to spherical coordinates. Well, x squared plus y squared plus z squared is rho squared. So the entire integrand function is reduced to e to the rho cubed. So those are the 2 steps that we need to do to convert this integral, convert the, or express the region in spherical coordinates and then convert the integrand. And then when I set up, I'm not going to forget that the dv has rho squared sine phi and then the differential unit. So I put my integrand e to the rho cubed, I've got my rho squared sine phi, and then d rho goes between 0 and 1, d theta goes between 0 and 2 pi, and d phi goes from 0 to pi. All right, now let's compute this iterated integral. I'm going to integrate with respect to rho first. Notice that u substitution will work really well here. The derivative of rho cubed is 3 rho squared. I'm going to try and do it in one step. I know that the antiderivative of e to the rho cubed must have an e to the rho cubed. And let me just think about how chain rule produces a rho squared on the outside. It produces a 3 rho squared. So to compensate, I'm going to put a 1/3. And of course, the sine phi is just a constant relative to rho, so I'm including the sine phi factor in there. Let me go ahead and finish the rest of the integral. It's pretty straightforward. And then I'm going to check my answer using Wolfram alpha. So after I've performed everything, I get an answer of 4 pi over 3 times e minus 1. And let's see what Wolfram alpha says. I've typed everything into the triple integral calculator. I've seen that the Wolfram alpha interpreted it correctly, and I think I see that I get the right answer. Yep, 4/3 e minus 1 times pi. Okay, in this example, we're going to see that spherical coordinates are actually really good with dealing with cones and, well, certainly spheres. So they're asking us to find the volume of a region that is above a cone, and you can see there that's the Cartesian equation of the top half of a cone. There you go. And below this sphere. So above the cone, or sorry, inside the sphere. So I draw a sphere of radius 1 and the cone. And I had to imagine what this sort of produces. It gives me sort of like a little ice cream cone looking thing. So I'm looking above this cone and inside the sphere. So it's this solid region that's capped on top by the sort of the North Pole portion of the sphere, and then underneath by the pointy part of the cone. I'm going to use a triple integral to compute the volume just by putting 1 in the integrand. But spherical coordinates are going to be preferable here since I've got a sphere and a cone. So let's try and figure out how to make the blue region in spherical coordinates. So first I can think about the theta angle. I think that's the easiest one here. You see that this object is sort of like fully circling the positive z-axis, right? There are points in this cone that range from 0 to 2 pi relative to the theta angle. So I do see that. The radius of, the rho value of any point in this region, like let's just mark a point in the region and connect it to the origin, I can think about how those values range. You've got the tip of the cone has a rho value of 0, you've got any point on the cap part having a rho value of 1, and then anything in between is going to have a rho value that's somewhere in between 0 and 1. So with that, I'm getting that rho ranges between 0 and 1. Now, if I just left it like this, then I would get the full sphere, basically, right? So if I allow theta to circle around from 0 to 2 pi and rho to be bounded between 0 and 1, without bounding the phi value, I would just get the full sphere here. But the phi value I can see is contained within the cone. There are a number of different ways that I can deduce what phi value is actually being bounded here, but I'm going to take the algebraic perspective. So I see that the cone is, in Cartesian coordinates, this expression here. And I also know what x and y are in terms of spherical coordinates. So simplifying this by factoring out a rho squared sine squared phi, I get a sine squared theta plus cosine squared theta, which makes a 1. So after I perform that algebra, I get this right here. Okay, so confining the phi to a first quadrant angle and the rho to a positive rho value, then I can cancel the square root. Actually, not just first quadrant angle, but first or second quadrant angle. So I'm looking at z equals this quantity describes the cone. I also know what z is in terms of spherical coordinates. It's rho cosine phi. So the Cartesian equation of the cone has given me a spherical equation, which is rho cosine phi equals rho sine phi. So canceling the rho gives me that cosine phi equals sine phi, and looking at the picture, I see what phi angle I'm talking about. This is the phi angle pi over 4. So this is the equation of the blue cone over there. And we saw that setting phi equal to a constant gave us a cone, and this is one way of determining which phi value represents this particular cone. So let me come back up here describing the blue region. I understand that the phi's in this blue solid are confined to 0 and pi over 4. As the range. Okay, so this is a description of the object. Now I'm ready to set up a triple integral to find the volume. So as I mentioned before, what we do to compute volume using a triple integral is putting 1 into the integrand. And then I'm just going to put the limits on the spherical coordinates in the appropriate integrals, and I never forget my unit rho squared sine phi when I'm integrating in spherical coordinates. So rho ranges from 0 to 1. Theta ranges from 0 to 2 pi. And phi ranges from 0 to pi over 4. Okay, and then you can do the work to get the answer here. There's no there are no really difficult steps in this iterated integral. It's good practice. I'll probably go to Wolfram Alpha and see what happens. Okay, here you go. I'm getting, this as the answer from Wolfram Alpha. It's not a bad practice to go through computing the iterated integral. You'd first integrate with respect to rho, then theta, then phi, but each of those computations is nothing really involved.